Kinematics equations of motion. To facilitate this conversation, I would really like to have a graph, okay? So bear with me for a second. I'm going to ask you to sketch this graph as well. It's going to be a VT graph, and I would like it to intersect with the vertical axis above the zero, okay? And so we'd like the run for this graph to be delta t. We're just going to label it up with variables, not with numbers, because we're going to use some of these variables in the derivation. It's going to start at an initial velocity of v1, and it's going to go up to a final velocity of v2. And again, I'm just using variables, no numbers, okay? Now for this derivation, I'm going to drop using all the arrows over top of the vector variables, just because it's going to get a little bit tedious as we go through and write everything, okay? So just so you know, yes, I know I'm doing that. You can do the same for the purposes of this. A little bit of background information. We know that for a VT graph, slope is acceleration, and we can calculate that as delta V. Oh, there you go. I even accidentally put arrows on there. Delta V over delta T. We also know that area of a VT graph is displacement, yeah. And something that you may not have thought of before, but I hope makes sense to you. If I was finding the average of two values, doesn't it make sense that I could say value 1 plus value 2 divided by 2 is their average? This is a mean. You know, we've talked about this in past grades, so it's not going to disappear now. So nothing new there, but we haven't really talked about it before, I suppose, but it's true still. Okay, and with that background information, I'd like to start deriving really simply what we're going to call equation 1. And this is the short, sweet one. Equation 1, I'd like to make use of, can that please go away? No food in class. Thank you very much. I'd like to make use of this guy here. I said I wasn't going to do the arrows, but I feel compelled to. I can't help myself. And I'd like to expand out this delta V to write it in full. Oh, there. V2 minus V1 rather than delta V divided by delta T. Well, I'd like to isolate for V2. Okay? So I want to get the delta T with that A there. So multiplying both sides by delta T, I'd end up getting A delta T equals V2 minus V1. And then again, since I would like to isolate for V2, I'm going to add V1 to both sides. And we end up getting V1 plus A delta T equals V2. And stylistically, we like to have the isolated variable on the left and the other mess on the right, the rest of the expression on the right. So V2 equals V1 plus A delta T. And bingo was his name-o. We're going to call that equation 1. Okay? Nothing really earth-shattering. Want to try and get equation 2 now. I would say equation 2 slightly more exciting. Okay? Slightly. Equation 2. I want to make use of what we said over here. Point number 2. Point number 2 says that the displacement is really the area under a VT graph. And so I don't want to be terribly technical with my notation here. I just want to say there's probably a rectangle-y bit over there in that graph. See if I segment it up like this. There's a rectangle-y bit. And so I can find the area of the rectangle bit. And there's a triangle bit right up there. So if I can find the area of the rectangle bit and the triangle bit and add them all together, I'll get the total displacement. And so let's throw in some variables here. That's the Mickey Mouse sort of cartoony approach to an equation. Let's throw in some actual values, or some actual variables. To calculate that rectangle, it's going to be height times length. The height here, really, of the rectangle is V1. And the length would be delta t. So V1 delta t, that's the area of that rectangle. To get the area of the triangle, remember it's 1/2 base times height. So I'll throw the 1/2 at the beginning. And the base is delta t. The height, though, might take a little bit of thinking. It's not V2. The height of that triangle is V2 minus V1. So I'll put it in brackets. Whoa. Brackets, V2 minus V1. Now I can go through and I can do a little bit of simplifying here. I can multiply through the brackets, and we know how to do that. 1/2 delta t times V2 minus 1/2 delta t times V1, but I want to write it in a particular order. So I'll write V1 delta t plus 1/2, instead of delta t V2, I'm going to say 1/2 V2 delta t. Because you know the order of multiplication isn't particularly important. Okay? No matter what order we multiply these things together in, you'll get the same answer. And the reason I'm doing that is because I got a V and a T, a V and a T. We'll keep them sort of in the same sequence for similarity. Minus 1/2 V1 delta t. All right. Now at this point, I would like to collect like terms. And when I say like terms, you know, one of these things just doesn't belong here. One of these things is not all that the same. Can you guess which one just doesn't belong here? Well, here it goes. Quick before I'm done my game. You know that Sesame Street song? Really? Oh, sort of. Anyway, we know which one doesn't belong. The other two are similar terms or like terms. So we can cluster them together, and we write V1 delta t minus 1/2 V1 delta t plus 1/2 V2 delta t. And if I've got V1 delta t minus 1/2 V1 delta t, how many V1 delta t's do I have? Half, yeah. So I say delta d is equal to 1/2 V1 delta t plus 1/2 V2 delta t Now, I've got some similarities, again, between these two terms. I've got a factor of 1/2 in there, and I've got a factor of delta t in there. So what I'd like to do is factor out 1/2, and you'd think I'd want to do 1/2 delta t both out front, but you'd be wrong. I want to do this, 1/2 times V1 plus V2, and then I'm going to factor out the delta t as well, but I'm going to sort of pop it on the end of the brackets. Because we said before, the order of multiplication doesn't really matter, even though I know we've talked about the distributive property and multiplying variables through brackets. But I can put it just as easily at the end. It really makes no fat load of difference. But there's a reason I want to do that. 1/2 times V1 plus V2 could be rewritten as V1 plus V2 over 2 times delta t. And now I could say, does V1 plus V2 over 2 look familiar to you? Have you seen it anywhere else on this page? Yeah?
It's the average velocity.
Yeah, it's this guy right up here. We talked about it previously. V average is V1 plus V2 over 2. And so now I could say, all right, so delta D could be written as V1 plus V2 over 2 times delta T, or we could just simply say delta D, if somebody tells you the average velocity, delta D is equal to V average times delta T. Okay, nice, sweet little derivation. And so some people, we're going to say that we have 5 equations of motion. Some people like to call this guy here equation number 2, and they kind of pop this guy to the end and say, oh yeah, that's equation number 5. We're going to say that we've done equation number 2 and 5 now, okay? Equation number 5 is kind of like the ridiculous cousin of equation 2, just recognizing this property. Yep.
A bonus equation?
Yeah, bonus equation, one of our 5 equations of motion. It's the extra one. Oh yeah, and then equation number 5, okay? I want to do equation number 3 though. Equation, actually, you know what, maybe I'll leave this sheet up here. Equation number 3 is not all that different from equation number 2, and I'll show you what I mean by that. We start off in the same way, with this kind of Mickey Mouse approach. Delta D, oh I should label this up, equation number 3, delta D equals exactly the same way, the area of the rectangle plus the area of the triangle. So yeah, rewrite it again. And then exactly the same way again, we're going to say, okay, so that's the same as saying delta D equals V1 delta T plus 1/2, pardon me, 1/2 delta T times V2 minus V1. Now I'd like to do a little aside, okay? And at this point, I usually like to sort of think to myself, when we're talking about doing V2 minus V1, V2 minus V1 is really the same thing as saying A times delta T. Okay? And so I'm going to sub that value into the expression that we've got so far. So we could just say we're going to sub in, we could say we're subbing in equation 1 into this expression, but I'm not going to be that detailed about it. Delta D is equal to V1 delta T plus 1/2 delta T times, now this is where the substitution comes in, instead of saying V2 minus V1, times A times delta T. Nobody says 1/2 TAT. What do they say? What would be the common way to write this? Not 1/2 delta T, A delta T. How should I put it on paper? Kevin? Yeah, I like it. A delta T squared. And this is an equation you use quite a lot. Delta D equals V1T plus 1/2 AT squared. It almost becomes like this rhythmic chant, you know, like delta D equals V1T plus 1/2 AT squared. It's going to be something that sticks with you because it comes back over and over and over again, okay? We're going to call it equation 3. You know that Polly Pocket commercial? Box it, lock it, put it in your pocket, bring it back out and play with it later, okay? That's a while ago, I know. It's from when my little sisters were young, I guess. But we're going to put a box around it, lock it up, pull it out when you want to play with it later, okay? All these guys were putting boxes around we're going to use later. One thing I want you to notice, though, and the reason I'm bringing it up now is so that later on you can say, oh yeah, remember when he said blah, blah, blah? This is one of those things, okay? You're going to say, oh yeah, I remember when he said that. If I take this expression, that's the formula. I'm not changing that formula, okay? But if I took that equation and I took the delta D over to the other side of the equal sign, so I had 0 equals negative delta D plus V1 delta T plus 1/2 A delta T squared. And I said, hey look, there's a T squared on that one. And there's a T on that one. And there's no T at all on that one. Think about what I'm saying here. I could put a box around that 1/2 A. And I could put a box around that V1. And I could put a box around the negative delta D value. And if I came along and I said, oh, I want to rename what's in each of these boxes as C, B, and A. What is this? I want to hear from somebody I haven't heard from in a while. I see the wheels turning. What do you say? What is it?
Simple form.
It's a simple form of what?
That AX plus.
AX squared plus BX plus C?
Yeah.
What's the magic name for that? Starts with a Q. Quadratic. Starts with a Q, rhymes with quadratic. It is quadratic, yes. Okay? This is a quadratic. If you know the A value, the B value, and the C value, you can use the quadratic equation to find the T value. Otherwise, it's very difficult to find the T value. Okay? That quadratic equation could be useful to you one day. And so I wanted to present this to you so that you guys could come back, look at this, and say, oh yeah, I remember when he said that. I know the delta D value, I know an initial velocity, and I know an acceleration in this situation. I could use the quadratic. That's very doable. That's grade 10 stuff, and I'm in grade 11, practically an adult now. No problem, okay? All right, let's try the fourth equation. Oh, I didn't ask. Can I take that away? Okay. Let's do the fourth equation. All right, so equation number 4. Equation number 4. I want to start off with what we called equation number 1 initially. It was V2 equals V1 plus A delta T. Little bit of algebraic gymnastics later, would you believe that I could get this to be expressed as delta T equals V2 minus V1 over A? Believable? Ripley's believe it or not. I believe it. Okay. Now I would like to take this value and sub it into what we called equation 2. Okay, so we're going to take a rearranged version of equation 1. You know, the math type people will call it equation 1 primed. And we're going to sub it into equation 2. Okay. And delta D equals V1 plus V2. Oh, I suppose it's equation 5 the way we express it. Let's call it equation 5. V1 plus V2 over 2, I'll put it in brackets even, times, now instead of writing delta T as we did in equation 5, well, this is the way equation 5 looks, we're going to write it as V1 plus V2 over 2, not times delta T, but times V2 minus V1 over A. Everybody who multiplies fractions together for a living knows that I can multiply the numerator straight across for 2 fractions, and I can multiply the denominator straight across for 2 fractions. Now, the denominator, not a problem. You just get 2a. The numerator, on the other hand, instead of writing v1 plus v2, I could have written it as v2 plus v1 times v2 minus v1. And maybe that makes the pattern pop out a little bit better for you. What's the pattern there? It's the initials are DQ, but it's not Dairy Queen. Yep.
It's a difference of squares.
Difference of squares. You got it. Anybody remember what difference of squares looks like if I have v2 plus v1 times v2 minus v1? It's grade 10 math. I know it's been a long time, right? It's the outcome comes as a result of foiling these 2 binomials as you've been doing for some time now. Yeah?
You just multiply the first 2 terms and the second 2 terms?
Yeah, you do. The first 2 terms, v2 times v2 would be v2 squared, and v1 times v1, v1 squared over 2a. And if you want to check out that that pattern works, go for it. We're using this as previous knowledge from grade 10, but what you'll find is that using this pattern, the 2 variables added together and then one subtracted from the other, you end up getting this to pop out every single time. Difference of squares. So we get delta D equals that. Now, most people don't like to leave these types of equations with a denominator if they can avoid it. So let's bring the 2a over to the other side. We're going to multiply both sides by 2a, and you end up getting 2a times delta D equals v2 squared minus v1 squared. And again, many people like to get one variable only on one side of the equal sign. In this case, they like to have the positive one, so it's going to be v2, not the negative one, which is the v1. So we take the negative v1 squared over to the other side, add v1 squared to each side. We get v1 squared plus 2a delta d equals v2 squared. I'm going to go up here just to give myself a little bit more room and rewrite it. v2 squared equals v1 squared plus 2a delta d, and I don't really know why I took myself all the way up there, because that's it. That's your gosh darn equation 4. Okay? 4 equations of motion. Beautiful. Okay, actually 5 equations of motion, because we got that other one that's sort of implied using the average of v1 plus v2 over 2. Would you like to have all 5 in one spot so that we can sort of take stock of things? Okay, let's do that. Let's put them all in one spot. So, equations 1, oh, did I take it away too fast? Okay, I'll leave it there for a second. But I'm going to bring out a new piece of paper. Equation 1, we're going to call v2 equals v1 plus a delta t. And this time I'll put the vectors over top, okay? Because we're not in derivation mode here. Equation 2 is delta D equals V average times delta T. Equation 3, or what we're calling equation 3, is delta D equals V1 delta T plus 1/2 A delta T squared. Equation 4, one we just did, V2 squared equals V1 squared plus 2A delta D. And then equation 5, that one that we're kind of going to call a bonus equation because it's really equation 2, but recognizing that V average could be found another way, is delta D equals V1 plus V2. I guess I should have arrows over top of those guys as well. V1 plus V2 over 2 times delta T. And we could put brackets around that V1 and V2 if we wanted to. It's kind of overkill really though. 5 equations of motion. Now some people like to say, why do we have 5 equations of motion that seemingly deal with like all the same variables? Now if I'm dealing with a problem that only gives me, let's try this out, V1, acceleration, and delta T, and I would like to find displacement, what's an equation that might fit that requirement? I'm trying to find displacement. I know V1, A, and delta T, but I don't know V2. What's an equation that might help me find displacement? Yep. Number 3, let's check it out. I want to know delta D. That's there. I know V1, I know delta T, I know acceleration. Bingo. That's good. I like it. Now I could find displacement then. What if I wanted to know V2 and I only knew V1, A, and delta T? What's a nice equation for finding V2? Yeah? The first one? I like it. Now what if I found the D, as Jacob suggested, and now I knew all 4 of those? And then somebody says, well, why don't we find V2? I've got all 4 of those things and I want to find V2. Those are my knowns. What's an equation I could use? Yeah? Sorry? The third one? Yeah, I could use the third one. Absolutely. Oh, not the third one. There's no V2 there. I could use the 4th one. I could use the 5th one. I could use the 1st one. It actually opens up the door to a lot of opportunities, right? Like we have a lot of opportunities now. And some people are going to say, does that mean that there's like 2 or 3 different ways to solve this problem? Absolutely. It's okay to have several ways to solve an individual problem. It doesn't mean that there's wrong ways or right ways. Sometimes there's better ways, easier ways. I can definitely see there's some equations there I would have fun tackling and some that are just kind of like, really, do I have to do that? That's okay. Develop strategies. That's what this is all about, okay? It's not about having right ways to do things.